Yeah, so apologies for the title. I mean, maybe I should have just said something about, new developments in matrix product states, and then people would have had a better idea what to connect this to. This is based on 2 papers. I mean, sorry, this is all on the bottom of the screen. A rather old one with Alex Monraz, where a lot of the questions that I'm going to discuss were formulated, and a more recent one with Markov and Josep Lumbreras. And that's the reason why I'm talking about this, because we actually made some progress on some of those old questions. If you're worried about the cockroach here, this is not going to appear very much in this talk. If you want to know why it is here, you have to read this paper. So this is going to be a selection of things which are sort of more interesting nowadays. So I want to start a little bit more sort of philosophically. If you observe a long sequence of data, I mean, your basic instinct as a scientist, well, you're looking for a pattern, right? So kind of a lot of what we do and what people do nowadays is kind of looking for simple explanations for large amounts of data. And so to make this a bit more concrete and have a more mathematical take on this, let's just look at a time series of observations. So it's discrete time, and also the observations are discrete, so it's all finite. For simplicity, I'm going to assume stationarity of the distribution. I mean, there is an underlying true distribution, even though I may not know it a priori. So that's kind of shift invariant under time, even though that's not absolutely necessary for what I'm going to say. But it makes our life simpler, because then we only have to look at the stationary properties. And so in particular, these finite marginals of like words, U underbar is a word from this kind of alphabet, as I call it. These probabilities, these are finite marginals of the infinite probability distributions, so they determine uniquely the distribution. So this is really what we're treating with. And so one kind of explanation that you might look for, because you're seeing this as a time series, you think, well, I mean, maybe there's some kind of temporal process that actually generates those things. And so you're seeing these U's, but you're imagining there are some X's that are evolving out of view, some kind of a hidden cause that generate over time those U's. And well, of course, I mean, to do any kind of analysis, you need to specify the nature of this causation and what this memory, these boxes here are. But I mean, this is basically what the rest of the talk is about. And well, okay, this is, I mean, basically we're going to fill these boxes with a finitely correlated state, or which is almost the same thing, a matrix product state. A physical example of this is, like, I stole this picture from some presentation of Serge Haroche. I think maybe this was from his Nobel Prize speech. The hidden causation, the memory is this cavity, and a sequence of ideally identically prepared atoms passes through this. They interact with the cavity that keeps a memory of the past interactions. When they come out, they can be observed, and in these U's, those would be those observations. I mean, they would contain, of course, also the kind of measurement that was done here. Maybe you have different settings, and the outcome. Okay, so one of the questions you might ask is, for example, can you infer the quantum nature of this hidden mechanism just by observing the classical probability of the outcome? How would you do that? Well, within this framework of hidden causation. Okay, so the rest of the talk has 3 sections. I want to discuss basically classical quantum and very general memories, and then a little bit of mathematical theory of linear algebra and convex structure. And then the last thing is I want to show, that's the main thing, that these different levels of explanation, they have strictly different power. So let's just go into this. So since I'm talking only about a classical stochastic process, in fact, the main intuitive background that you should have is not matrix product states, but hidden Markov chains. Because, I mean, hidden causation, the simplest process is a Markov chain, and then these U's are just function of the Markov chain. So an abstract way of saying this is, well, these boxes here, they are stochastic maps that map the memory to the memory and an output, and we do this in every time step. And stationarity is sort of, like I said, it's maybe not the most fundamental property, but since I assumed it, this has to do with an eigenvector with a fixed point condition. So if I trace over those u's, I get a map from x to x, a stochastic map. It's just finite alphabet. And so this, I call this d bar, and this has to, well, it has to be a stochastic map. So in the convention of probability vectors are row vectors, and observables are column vectors. So the d bar acting on the identity, which is like the trace, maps to the identity, and d bar acting on the other side on a particular distribution fixes this distribution. That's the stationary distribution of the process. And then you can write the probabilities basically as a long matrix product. Namely, you have these kind of, for each u you have a substochastic map that takes you from the memory to the new memory state. You just multiply them up, and you apply on the one hand your identity, and on the other hand the stationary state. I mean, or a probability. Yeah, so I'm using here probability convention. Like I said, the matrices are true matrices, and stochastic matrix means that the row sums are 1, not the column sums. And so they act on the identity, and then this pi is like a row vector on the left-hand side to contract it. Yeah, and this is basically a hidden Markov chain. And this is kind of a fundamental problem in information theory, in data analysis, in machine learning, to, for example, infer something about the Markov chain from these observations here. Or to even to calculate certain characteristics of this U sequence even if you know the Markov chain. Yeah, so the quantum version of this is, well, we're still observing classical values, but this axis, this is now a quantum system. These are states in a quantum system, and of course I would like this H to be a finite dimensional system. And then these DUs are just completely positive maps, such that D bar is unital, preserves the identity. So again, I'm inheriting Heisenberg picture from the probability notation. The maps act on observables. The nice thing is that, well, actually I didn't advertise this before. The nice thing is that when I form the matrix product, I keep the same order, right? So this is actually the temporal order. I see first U1, then U2, etc. And so I get the same ordering of the matrices by acting on the identity and by thinking of the state as a linear function, basically. Yeah, so it looks kind of basically the same. The mathematics is exactly the same. And so this, in the language of matrix, in this matrix product world, this would be called a finitely correlated state. In fact, a C-star finitely correlated state, because my memory, this X here, that's a quantum system. And so those maps here are completely positive maps in the usual sense of, I don't know, Choi matrix, positive semidefinite. And so yeah, this is kind of what this picture is described by, actually. Yeah. But of course, I mean, looking at these two examples, you see, like, I mean, obviously to write down the probability law, I needed very little. I just needed elements of a vector space. I need a linear function, and I need maps. Okay, so let's just abstract it wildly. I didn't do this. I mean, this was done in the 60s in classical probability. So those x's here, they are just elements in a vector space. I mean, this kind of, I mean, to write down this law here, this formula, that's just linear algebra. So I didn't actually need that, I mean, quantum theory. So let's just try our best to abstract this. These are elements in a vector space. D is a collection, these DUs are just linear maps. And I need some kind of analog of the identity. I call this here tau, and I need an analog of the stationary state. I call it again pi. So that this D bar, so when I trace over the observation, I have a genuine evolution of some kind of these elements of V. And so I basically just abstract this formula. I say, well, the identity is just an element in a vector space. The pi is just a linear function on that vector space. Okay, fine. I mean, I need real vector spaces and so on to make these real numbers. And so that's all fine. If you're starting from the process and you say, and your question is, can I write it in this form? It's not so fine if you, well, and this is called a quasi-realization. And in the language of Fannes, Nachtigall, and Werner, from this paper from more than 30 years ago, they call this a general finitely correlated state, actually with an abelian observable algebra, because we are only seeing classical outcomes for the moment. I mean, maybe at the end of the talk I will comment very briefly on quantum finitely correlated states. Yeah, so this is all fine if you're looking for this as an explanatory mechanism. Well, at least maybe not even explanatory, just a way of condensing all these probability margins into some small number of data, because now, if this is possible, you only need matrices over this finite dimensional vector space, hopefully it's finite dimensional, and some vectors. So it's all, I mean, like, given the dimension D, or R, let's call it R, there's just a finite list of numbers that describes all of this. So this would be a fantastic condensation of your infinite chain. So it's there is a catch though. So kind of it doesn't really go very easily the opposite way, which is why these kind of things are not. They don't lend themselves easily as a variational ansatz to optimize your fit. You know, you're saying, okay, maybe I hope that the rank is 10, and I'm just trying to optimize an approximation here. For that, you would have to make sure that these expressions here are always non-negative. And that's not guaranteed because I'm just doing linear algebra. I have no positivity structure here. In fact, there cannot be a solution because in the worst case, it's known that it's undecidable. So there's a reduction to the halting problem. You can code the halting problem of Turing machines into a bunch of these matrices. And the machine will halt if you eventually encounter a negative probability, and it doesn't halt if they're all positive, non-negative. So that's very disappointing and very dispiriting, and saying, well, okay, I mean, maybe that's not very good. But we'll get to this. In fact, there is an additional structure, which of course is also undecidable, but that somehow saves us. Okay, so I want to do some simple examples before we go on. Probably the simplest example of this is actually not a hidden Markov chain, it's a Markov chain. And the simplest Markov chain is one without any memory. So it's just a memoryless distribution. All the UTs in this finite alphabet are identically distributed and independent. So the distribution is this infinite product of single letter distribution, P1. And so obviously, I said it already, this doesn't require any memory. And well, sometimes you can be lucky, but of course, normally you're not. So what are examples where you do need memory? Well, the simplest example I can think of where you can kind of see how the memory is necessary are those so-called definite distributions. So these are, I mean, also known as infinitely exchangeable distributions. So those are convex combinations of these kind of things. So I have px's on the single letter, and each of them is actually realized as an infinite tensor power. And then I just make a mixture of those. And this is pi x is chosen deliberately. This is actually the stationary distribution. So this is generated by a hidden Markov model, and also, of course, in this more general sense, because you just have to memorize this x forever, and then given x, you output a sample u according to distribution px. And in fact, you can see from, I mean, if those px's are distinct, are mutually distinct, you can show that you actually need a dimension of this memory system equal to the cardinality of x. Simply because those states here, these states here, they are perfectly distinguishable. They are mutually orthogonal in the infinite limit. And so for x and infinite alphabet, you can this gives you examples of stationary processes that definitely cannot be realized with a finite memory. So there is, I mean, the thing with the finite explanation, that has to come from somewhere. And so let's go into this. Well, actually, sorry, I have another example. Let's see if I have enough time for all these examples. I have another example that's a bit more quantum. So the vector space is actually, that corresponds to the qubit. So it's self-adjoint operators on a two-dimensional Hilbert space. The state is the maximally mixed state. The identity is the identity. And then we have a bunch of operations. So we have, for example, projection onto zero state, like spin up, set, spin up, spin down. We have rotations around x and z, and we have even the transpose, so that I show you something that is not even completely positive in the usual sense, but you can mock it up with something completely positive. And so this comes from the paper with Alex Monraz. When the alpha and beta are commensurate with pi, then by iterating these rotations, you get arbitrary angle rotations around the x and the z axis. And so by composing those, you get arbitrary close to unitaries in the, I mean, you approximate the whole SU2. And so you can actually realize the resulting process, which has 1, 2, 3, 4, 5 symbols. So the U alphabet is 5, with a 4-dimensional this is just saying that the quasi-realization is 4-dimensional because it's a 4-dimensional vector space. It requires 2 qubits actually to make it in as a completely positive, as a quantum hidden Markov model. And you can do it with 1 qubit if you remove that last one. And you can even reduce the dimension if you remove that one here, if you only have the x rotations, for example. Oh, wait a second, I want maybe the z rotations. Well, okay, never mind. I mean, I can also restrict the dynamics just to the equator. So you can cook up slightly simpler examples from this. Well, I don't want to talk about the recoverability problems. I just want to talk about the structure now. So let's talk about how we get positivity. So in the classical and the quantum case, this is enforced by the structure of additional structure in the vector spaces, because we have positivity. We have a notion of positivity both in probability theory, it's basically just that all the entries of a vector are non-negative, and in quantum theory because it always reduces to some positive semi-definiteness. And so in general, we have that we need to assume kind of that we have convex cones in the vector space and in its dual, such that the unit is in the cone and the stationary state is in the dual cone, and that these cones are preserved under those transformations. Then you get that the probability is positive. This is kind of abstractly what's going on in quantum mechanics, where these cones are just the positive semi-definites. Yeah, so by the dual cone, I just mean all the functionals on the vector space which evaluate non-negatively on the cone C. And in fact, this is not just sufficient; it's also necessary. If you know that your linear algebraic data produce non-negative probabilities, so if we have this, then we can construct such cones that are preserved under those maps. And the simplest one is, for example, you just take the unit and you act on it with all the evolutions. And this is a U bar, so this is a string of maps. So it's U1, U2, and so on in any length of succession. So it's a countable infinite set of elements in the vector space, and you just let the cone generated by this. And in the dual space, you act with those same maps on the stationary state. And because you get positivity, you know that those two cones are actually dual to each other. So they kind of any element from here evaluates non-negatively on any element from here. So in general, this is not unique, but that's a different topic. And so, yeah, an interpretation of this is that in the finite-dimensional case, a finite-dimensional quasi-realization. So this is just this vector space. We suddenly get this cone there. So what is this? So I mean, in my limited work for foundations of quantum mechanics, I encountered such thing in the form of general probabilistic theories. So the C and C prime, they are pointed and generating cones in the general probabilistic theory. The unit must be in the interior of the one cone. We have a set of states which are all the linear functions that are one evaluated on the unit, and we have somehow kind of P of M elements. These are the elements in the cone which are between 0 and the unit, because they can be, I mean, those P of M elements have to be positive and they have to sum to the identity. And so using this, you can actually write what's going on in this box here as a kind of an evolution in the general probabilistic theory. So you're coming in with a state, well, the true memory state after at time t is some ft, that's a linear function in this set here, and out comes another state given that we see a symbol here, and this is the formula here. This is sort of the abstract Born formula in the post-measurement state. we just compose the two things. There's kind of the du map here. We compose them. This will make something which is not in S because it doesn't evaluate to 1, but to less than 1. So we take out the constant that we interpret as a probability, and we get a new state. And so, yeah, I think I spent all my time on the pedagogical introduction. So now let's go to part 2. Consider now a general such process. So one thing that you learn in one part of the analysis of those processes, you can arrange those probabilities in a matrix, in an infinite matrix where the rows and columns are indexed by words over U, sequences over U, in this way. So the matrix elements are just marginal probabilities, where I juxtapose U and V. And so this means the same entry is actually repeated over and over again in the matrix. Fundamental observation is if the process has a quasi-realization of dimension D of this vector space, then I can write this matrix here in this way. I can sort of factorize the entry by first applying dV to the UV entry, I'm applying dV to the unit and du to the state. And so those are both, this is an element of V, this is an element in the dual, which is also D-dimensional. So the whole thing has rank D at most. And so the rank of this matrix, that turns out to be a key thing. So we can kind of see how this relates to the hidden Markov and hidden quantum Markov models that we had before. If P has a positive realization as a hidden Markov model, well, we have S states, so that the vector space is S-dimensional, because we just need to, like the probability densities over S elements. If it is a Hilbert space of dimension T in a quantum realization, well, then the matrices are T square dimensional, so D is equal to Z squared. And so we see that, okay, the finite rank of H is necessary for the existence of one of those finite explanations. So the question is it sufficient? Well, again, we know from work in the 60s in stochastic processes, yes, it is. If the rank is finite, then there exists a so-called quasi-realization with dimension equal to the rank of this Hunkle matrix. And this is the minimum possible by the previous argument. So there's sort of this kind of a big theorem in this kind of Hunkle matrix theory. Any other minimal dimensional quasi-realization is similar to this regular one up to linear equivalences. And so the construction is kind of trivial once you're not afraid of the infinite dimension. I mean, obviously H is an infinite matrix. It has columns of infinite length, but because it's infinite rank, those columns only span a finite dimensional subspace. So this is our thing. Our object is simply the column, the space spanned by the columns. That's our vector space. And we can basically write the maps explicitly in terms of shifting around in the matrix. So I'm not going to go into this because this is, supposedly old stuff. So yeah, next question is, okay, fine, assume that the rank is finite, so we know there's a quasi-realization. Does it mean that it's generated by a hidden Markov model? That means I can actually do this with a classical memory, not just this abstract vector space. And so this question was asked actually in the 60s and early 70s by Fox Rubin and Damadikari and Nadkarni, and they were the first to provide examples that have a process with finite Hankel rank, actually rank 3 in the example, but require an infinite classical memory to generate. So probably need to speed up. In fact, they define them as hidden Markov models with an infinite memory. I mean, their memory is like integers, and they have some dynamics on integers, and then they take a simple 3-valued or 4-valued function on these integers, and then they prove stuff about it. And the proof that you need infinite memory, this comes from basically spectral theorems in Perron-Frobenius theory about stochastic maps. Okay, so then you can say, fine, good, I accept this is also old stuff. There are processes that require infinite classical memory, but maybe I can do something with finite quantum memory. So yeah, so let's say the Hankel rank is finite. Is a process generated by a finite memory hidden quantum Markov model, so a finitely correlated state. And so as far as we can trace, this was asked actually in the very paper of Hannes, Nachtigall and Werner. And as far as we can tell, this has not been answered. Maybe because people didn't find it very interesting, but we did. Yeah, so that's it. Yeah, so officially now the question time starts. So you have to excuse me, I'll at least show you some new results. Yeah, so first result that we had in the paper is we looked at their processes. This the largest, the most general classes in the second paper by Damadikari and Nadkarni. Turns out they actually have quantum realizations, and in fact the whole family they describe, they all can be realized with qubits. So it means d equal 9, 3 squared. Okay. So the last thing I want to show you is kind of what's already written here. So it's very good. The full spoiler is already there. There are processes which have finite Hankel rank, so they can be explained by this GPT dynamics, but they cannot be explained by quantum mechanics. So that answers this question of Fannes et al. In the positive. There are such things. So yeah, the question is how much of this stuff I give you now. So yeah, so we can learn something about this quasi-realization, and in fact about the minimum one that I call the regular one, or the Damadikari et al. They call the regular one. There's this way of constructing ab initio from the Hunkle matrix, but there's also a way of obtaining it by basically a quotient construction starting from any realization, like one that has maybe way too many degrees of freedom. You can always reduce the number of degrees of freedom, and you factor out some kind of kernel that has to do with that the states that the dynamics explores don't really distinguish between certain observables. And so this is always isomorphic to the regular realization. But you also learn something about the cone. This cone that you need, if you start with a realization like a quantum one, this cone also is obtained by an intersection with a linear subspace and by taking a quotient. And so I'm not going to go into this, but for example, in the case of a classical realization, this cone that you get is a polyhedral cone. So a necessary requirement for having a classical realization of your process that there must be this polyhedral cone left invariant by the maps. And because in quantum we always start with the positive semidefinite matrices, if you do these quotients and so on, what you end up with is an object like this. It's a cone of, these are the coordinates in my vector space, such that a certain positive semi-definiteness condition is satisfied. And those R matrices, they are just big fixed matrices. They are data that I need to describe the cone. These are called SDR cones. These are sort of the natural domain of a semi-definite program. These are the feasible solutions, of a set of points satisfying a given set of semi-definite constraints. So if we do go through this construction, we learn that, okay, if a process has a quantum realization, there must be this semi-definite representable cone that is left invariant by the maps. And so the idea we had was, well, what happens if we can engineer things such that there is only one possible cone? Because that's the real undecidable part of the Sontag result, of the undecidability of positivity. There is usually much more than one possible candidate cone that you have to check. If there is only one possible candidate, in fact, we know that there is a minimum and a maximum one. So if those two things collapse, then we can just look at it and say, well, this is not a polyhedron, so it cannot have a classical realization. That's what Alex Monraz and I did with this example. The cone is simply the cone over a sphere or over a circle. So it's not polyhedral. A polyhedron has finitely many extreme points, so it says infinitely. Okay, cannot be realized. And so what we did in the newer work is we show an example of a process that, again, where the two cones are the same, but it's actually transcendental. It's in fact the cone hull of the exponential curve, like the exponential graph. The graph of the exponential function is transcendental, so the cone is also transcendental. And so because SDR cones are all semi-algebraic, described by a bunch of algebraic equations and inequalities, this cannot be realized quantum mechanically. And so the process is explicit. In fact, we start with the quasi-realization. So I'm not going to show you this because I'm out of time, I think. But it's kind of a very simple explanation that uses kind of the fact that we can by simple matrix multiplication realize both the additive group of numbers and the multiplicative group of the exponentials. That's kind of, that's kind of a nice trick. And And so, yeah, so this is the cone. The cone that we get is of this form. Like it's a three-dimensional thing, so you can visualize it. In fact, I think we produce plots, but they're not very illuminating. And so if you set y equal to 1 here, you see this just reduced to x is larger or equal than e to the z. So it's the epigraph of the exponential function, and you just generate the cone from that. There is kind of more example based on the power cone, where you have this kind of inequality, and when t is irrational, then this is also transcendental, so again, it cannot be realized. And so this is kind of the upshot. I mean, we are currently trying to generalize this into truly finitely correlated states, where the observation is a quantum state, but not a stochastic process. So there is a generalization of this order structure, which is called operator system, because you have to deal with ordering on your vector space, but also tensored with semi-definitely ordered n by n matrices. And so, yeah, so our hope is that maybe these kind of processes, okay, what's the upshot here? I showed you that, I tried to convince you that there is a stochastic process, well, in particular, a finitely correlated state, which is not a C-star finitely correlated state. So it's not writable in the way that usually people think like MPS, that there's this virtual quantum system. There's a virtual other system. So could this bigger class of processes or of states, if we can generalize it to truly quantum finitely correlated states, could that be an interesting class, for example, for a variational ansatz? So this is kind of, something down here. So for that to work, we would need to characterize the CP maps on these cones. So the kind of the order preserving maps on these cones, which is an ongoing project. But if you could, because that's, in the quantum C-star case, this is what choice theorem does for us. We can basically everything reduce to semi-definite matrices, and then we optimize over those semi-definite data. So if we could solve that problem, then we would get a potentially slightly larger class of objects to try to approximate a given state that you observe somewhere. So yeah, maybe something like this. And of course, another question is, can these exponential power cones may be useful for something else? I mean, one of the cool things about this is that the dual cone has the same form, and so you might think that this could be useful in numerical optimization for certain highly non-algebraic problems. We found a PhD thesis, I forget the name of the person, not so long ago, so people tried this. And so yeah, that's the end of the talk. Sorry for running a bit over time, but that's it.
Do we have questions? Okay, maybe I ask a question. So you said that for definite distributions, the memory is of the order of x, the number of alphabet, right?
Yeah.
And you said the states are orthogonal, that's why, or what was the reason? You said
I mean, you can see from the fact that when you look at the infinite tensor product, like p to the power infinity and q to the power infinity, they are ideally distinguishable when p is different from q. So from that that's kind of one argument to deduce why you need a different memory state for each of those components in this example here. Yeah, why you need a different orthogonal symbol in the memory, because the states are orthogonal, each of these tensor power states.
Okay, if there isn't any questions, let's thank Andreas.